Welcome back to water quality in the Pacific Northwest. Today, we are continuing to talk about drinking water in the United States and specifically in the Pacific Northwest. Uh, Basically, we have 5 lectures on drinking water, and we are covering the 5 components of drinking water. We're talking about the Safe Drinking Water Act, sources of drinking water in the Pacific Northwest, the public perception of drinking water contaminants, and drinking water treatment. In Lecture 28, we covered the Safe Drinking Water Act and sources of drinking water in the Pacific Northwest. In Lecture 29, we talked about the public perception of drinking water in our region, the 4 Pacific Northwest states, Alaska, Idaho, Oregon, and Washington. Today, we're going to start talking about drinking water contaminants. This will take us a couple lectures to cover the contaminants, but this is a very important aspect of drinking water quality. The first thing I'd like to talk about are drinking water standards. I want you to remember from the last lecture that if you get your drinking water from a public water system, there are regulations that exist that protect the quality of your water supply. On the other hand, if you're a portion of that 18% of the American public that gets your drinking water from a private water system, probably a private well, there are no regulations that are enforced, and we have the concept of user beware. In addition to that, there are guidelines that you should follow if you have a private water system, but they're not enforceable. If you need help with these regulations and the idea of what contaminants you should test your private water supply for, there are several sources of information. You can go to your state government, you can go to your local health districts, you can go to University Extension or to the EPA, and they all produce pamphlets that tell you how to go about protecting your water supply. Okay, for the 82% of Americans that live or communities have to test their water on a regular basis to make sure that they meet standards. If they have a contaminant in their water that's higher than standard, the public water system has to take steps to rectify that to ensure that your water is safe at the tap in your home. So EPA regulations are divided into 2 categories. We're going to start with the primary drinking water standards. These are enforced. They specify the maximum contaminant levels of a particular contaminant that can be in your water supply and you still be safe based on health-related criteria. These are research-based numbers. Except for microbes and nitrates, water exceeding the listed maximum contaminant level does not pose an immediate threat to public health. However, your local water district is required to take steps to rectify that problem. So there's several categories for primary standards. We talked about the 5 categories that are regulated in the last lecture. We talked about organic contaminants, inorganic contaminants, microorganisms, radionuclides, and I mentioned turbidity. There are 3 categories where we have good standards. We have good standards for some of our inorganic chemicals that we might find in drinking water, for the inorganic chemicals we might find in drinking water, and for microorganisms. So let's look at a couple of these categories and give you an example of some potential contaminants in your drinking water supply that your public water system has to test for and to make sure that everything is okay. So let's look at organic chemicals. Organic chemicals are a huge category. We have 3 types of organic chemicals. We have chemicals that are called synthetic organic chemicals. These are chemicals that are manufactured by humans. They're called SOCs, synthetic organic chemicals. We have a second category called volatile organic chemicals. We abbreviate them as VOCs. And I'll give you a few examples of each in just a few moments. And we have a third category of organic chemicals that we call the trihalomethanes, or the THMS. I've always only seen it abbreviated THMS because it's so hard to pronounce. So let's look at the primary standards for a few of the organic chemicals. Basically, this is a category that has expanded greatly since the Safe Drinking Water Act was first passed in 1974. As more research is done, the number of regulated chemicals in the organic category is rapidly increasing. That's because humans manufacture thousands of different synthetic organic chemicals for use in our daily lives. Sometimes these chemicals get into our water supply, and if research has shown that these chemicals are detrimental to human health, they are regulated. So let's take a look at each of these three categories of organic chemicals for just a few moments. So first of all, let's take a look at our synthetic organic compounds, or our SOCs. And this is the biggest category of contaminants that we are regulating in the United States today. These are human-made chemicals, and many of these chemicals are toxic to living organisms. So we have to have particular care. But these chemicals are used in the manufacture of many products, many agricultural products and many industrial products. In this category, we have thousands of chemicals. We don't have that many that are regulated right now because we don't have a lot of research on them. And a lot of the thousands of chemicals that are manufactured are very unlikely to leak into our drinking water supply, so we have less of a concern. I'd like to give you an example of three synthetic organic chemicals just to kind of show you what they are. First of all, let's look at the chemical aldicarb, a synthetic organic chemical. It is an insecticide used to kill insects. The health impacts are that it impacts the nervous system. That's how it kills insects. If aldicarb is present in our drinking water in high concentrations, it could have a negative impact of the human nervous system. We have a maximum contaminant level that we allow in drinking water of aldicarb, and that's 0.003 micrograms per liter. Our goal is to get, we have an MCLG, which is a goal. We would like to get that maximum contaminant level down to 0.001. So that's an example of one of the hundreds of different synthetic compounds. I just have this kind of a diagram that I think is interesting, that's very debatable. We have a federally enforced MCL, maximum contaminant level, but we also have a goal that we would like to have that maximum contaminant level to drop. So we can't really get to zero contamination, but we can get to a level that's so low it's very, very unlikely to cause any impacts. Let's look at a second synthetic organic chemical, chloridane. Chloridane is also used in agriculture. It's an insecticide. Research in the lab has shown that at higher concentrations, chloridane can cause cancer. So we regulate it because we don't want people to get cancer. We have a maximum contaminant level of 0.002 micrograms per liter, and our goal is to have absolutely nothing in the water because it is a cancer risk. So if there's an industrial process in your local community that manufactures chloridane, it's required that your public water system sample water routinely to make sure chloridane is not in it. If, on the other hand, you don't live in an agricultural area and there are no plants that use chloridane, you probably have an exemption, and your public water system doesn't have to spend the money and check for chloridane on a regular basis. And if we look at a third example of a chemical, we could go through this and list literally dozens and dozens and dozens of SOCs. Carbon tetrachloride. Carbon tetrachloride is a cleaning agent. It's an industrial waste. It's regulated because it's a cancer risk. Laboratory studies have shown that it causes cancer in mice. As a result, we have a maximum contaminant level of 0.005 micrograms per liter. And our goal, our MCLG, is 0, that we don't really want any of that in the drinking water supply. So if you live in a community where carbon tetrachloride is widely used or it's manufactured, your public water system probably has to test for it on a regular basis in the water supply. And if this is not used in your community, your public water system probably has an exemption. Each one of these tests costs money. And if your public water system is required to test for it, let's say 6 times a year, that starts adding up. You're probably going to spend a couple $1,000s doing that. If you live in the city of Spokane, it's no problem because there's 400,000 people that live in Spokane County. However, if you live in a rural subdivision with 40 homes in it, you don't really want to test for that all the time because it's very expensive. A second category of organic chemicals that are regulated are called our volatile organic compounds. These are also synthetic chemicals. The major difference between a volatile and a synthetic organic compound is that volatile organic compounds vaporize at room temperature. They vaporize from the water into the air. VOCs are used as degreasing agents. They're used in glues, they're used in dyes, they're used in paint thinners, and they're actually used in some pesticides. So they have a lot of utility for humans, but we don't want to get VOCs in our drinking water because research has shown several of the VOCs out there may be hazardous to our health. And let's look at a couple examples. First example is benzene. Benzene is an industrial chemical. We don't want high concentrations, or we really don't want any of it in our drinking water because laboratory studies have shown in small animals that it poses a cancer risk. Thus, we have an MCL, a maximum contaminant level that's regulated at 0.005 micrograms per liter. But we have an MCLG, which means we want 0 of benzene in water supplies. Another example of a volatile organic chemical would be trichloroethylene, which we abbreviate as TCE. It's waste that's generated by dry cleaners. It's a component of pesticides. It's used in paint. Research has shown that it will cause cancer in laboratory animals, so we regulate it so humans are not impacted by it. And we have an MCL, a maximum contaminant level, that's enforced of 0.005 micrograms per liter. And of course, we have an MCLG, a goal we would like to get our drinking water supply down to absolutely 0 concentration of TCE. Another example of a volatile organic compound is vinyl chloride. Vinyl chloride is present in PVC pipes. Laboratory studies have again shown that it causes cancer in small laboratory animals, thus extrapolated it could be hazardous to humans. We have an MCL of 0.002 micrograms per liter, and our goal is we don't want any vinyl chloride in our water. So I've given you 3 examples of synthetic organic compounds and 3 examples of volatile organic compounds. 3 of maybe 400 chemicals that are regulated. So there's a long list of chemicals that are regulated in the organic category. Now you have to remember, before the Safe Drinking Water Act, none of the organic chemicals were regulated. Remember, the Surgeon General and the U.S. Public Health Service never dealt with organic chemicals, so we had to wait all the way until we got to 1974 when the Safe Drinking Water Act was passed to deal with these chemicals. The third category of organic contaminants are THMs, trihalomethanes. They're created in water as byproducts of chlorination. When you chlorinate water or you chlorinate substance, THMs are produced. So when you add chlorine to other organic chemicals, you create THMs. Basically, they're byproducts of the reaction of chlorine and organic chemicals. THMs include things like chloroform, bromodichloromethane, and bromoform. There are quite a few THMs. They are regulated. To give you an example, let's look at total THMs. So a contaminant we can measure. It happens when you chlorinate water. Health risk, it's a cancer risk. Studies have shown that small laboratory animals do get cancer when they're exposed to high concentrations of THMs. So we have an MCL of 0.1 micrograms per liter, and of course we would really like nothing in our drinking water supply. Okay, so that gives you an example of some of the organic chemicals. Remember, it's a very complicated category, and it's the category that we're adding more chemicals and more regulations to all the time. So let's look at another category that we have regulated probably for 50, 60 years. These are our inorganic chemicals. There are many inorganic chemicals out there. Several of these inorganic chemicals you have heard about. Several substances are of public health importance. So inorganic chemicals can get into water, which then get into our drinking water supply as a result of natural processes. Our water is exposed to rocks. As inorganics weather out of rocks, they go into solution. There are environmental factors that can cause inorganic chemicals to be in water supplies, and a lot of human activity puts some of the inorganic chemicals into our water supply. So let's take a look at a few of these inorganic chemicals, why they're important, and how they're regulated. These are primary standards, which means that if you get your water from a public water system, your public water system has to test to make sure these inorganic chemicals are not present at high concentrations in your drinking water supply. So let's look at a few things that you're probably somewhat familiar with. Let's start with nitrate. Nitrate comes from several sources. It can come from fertilizers, it can come from sewage, it can come from animals, it can come naturally from the soil. We regulate it because we have a health impact that at high nitrate concentrations, infants can develop a condition called blue baby syndrome, where basically their blood is robbed of oxygen. Because of that, we have a maximum contaminant level established, a primary standard of 10 parts per million, 10 milligrams per liter of nitrate nitrogen. So communities have to test their water and ensure that it contains less than 10 parts per million nitrate nitrogen. This is really an interesting contaminant because the only humans that are really impacted by nitrate concentrations are infants, children that are less than 6 months old. And that's because of the digestive system. When an infant is less than 6 months old, when the infant eats, the food products are broken down basically by microorganisms within the child's system. However, when the child gets to about 6 months of age, the microorganisms are replaced by acids, which start breaking down the foods. So when you have the biology going on with an infant less than 6 months old, if the infant consumes too much nitrate, they can develop the nitrate is turned to nitrite, which attaches itself to the hemoglobin in blood and basically robs the baby of oxygen. We call it blue baby syndrome because when this condition occurs, the area around the nose and the mouth of an infant takes on a bluish tinge for lack of oxygen. Again, there are many things that, many places that we get nitrates in our drinking water. Probably one of the most common sources is nitrate fertilizers or nitrogen fertilizers. We buy commercially produced nitrogen fertilizers. We put them on our soils. If they run off our soils, they get into water supplies, and those water supplies may be our drinking water supplies. Same thing with Organic fertilizers. Organic fertilizers have nitrogen in them too. If organic fertilizers run off the land and end up in water supplies, they also put nitrates in our water supplies. So nitrate is a very important chemical. Most public water systems test for nitrate. Let's look at another inorganic that has been in the news quite a bit. That's lead. We don't see a lot of lead in natural water supplies, but many times we do get lead in our drinking water because of the fixtures that we have in our home to distribute water, the pipes. A lot of times pipes leading into the home are glued together with solder, and solder has lead in it. Under the right conditions, this lead can leach out of the pipes and enter the drinking water supply. High concentrations of lead adversely affect the nervous system, adversely affect kidneys in people, and high levels of lead are just generally toxic to infants. So we have an MCL. Our MCL is 0.015 micrograms per liter. Lead's been in the news because of Flint, Michigan in the last couple of years. People in Flint, Michigan have had their water supply contaminated with lead. Actually, the city didn't contaminate the water supply. The city bought a cheap water source, and that water was pretty acid. And when the water was distributed to homes, the acid leached lead out of solder in people's home pipes, and that caused the lead in the drinking water faucets. So we have a lot of older pipes that have lead in them, or at least are glued together with solder, which has a component of lead. Let's keep looking at some inorganic chemicals. Arsenic. Arsenic can be in your drinking water simply because the water comes from a source where the rock geologically has quite a bit of arsenic in it. Old-time pesticides, first-generation pesticides used arsenic. So if there's any pesticide residues, first-generation pesticide residues, they could get into water. If you live in a mining area, smelters sometimes put arsenic into the air, which will land in water, and other industrial waste. We know that arsenic impacts the nervous system, has a negative impact there, and because of that, we have an MCL for arsenic of 0.01 milligrams per liter. There are a lot of telltale signs for people that have arsenic poisoning. Here's a person with hands that are definitely a symptom of arsenic. We do have some areas in the western United States where the drinking water is naturally high in arsenic, and we need to test for arsenic, and we need to modify the water source so that arsenic does not injure people. A hot spot in the western United States, although not in the Pacific Northwest, is the Fallon area of Nevada. Let's keep going. Mercury. Mercury is another inorganic chemical. Mercury can get into water supplies if industrial wastes are dumping into these water supplies. The geology, particularly in some parts of the western United States, may have parent materials that have a little bit of mercury that leaches out of the rock and ends up in the water. And we have some fungicides that do contain mercury, or did contain mercury, and if they leach, they're pretty persistent in soils. If they leach into a water supply, it could be part of our drinking supply. So we have a standard for mercury, because we know that mercury adversely affects a person's nervous system and affects their kidneys. And we have a value of 0.002 milligrams per liter as our standard for mercury. Now, there's dozens and dozens and dozens of inorganic chemicals, and I just wanted to take you through a few of them. We can look at cadmium. Cadmium can get into water supplies due to the geology of the rocks in the local area. Phosphorus fertilizers. Some phosphorus fertilizers have a little contamination with cadmium. So if the phosphorus fertilizers end up in water supplies, there's probably going to be tiny amounts of cadmium. And in mining areas where we do some metal finishing, you might have some cadmium waste products that could leak into the water supplies. We know that at high concentrations, due to laboratory studies, high concentrations of cadmium adversely impact kidneys, and thus we have an MCL for cadmium of about 0.005 milligrams per liter. We can add a couple more. Fluoride. Fluoride can get into water from geology, from smelting, and sometimes we add fluoride to drinking water. We know that we don't want too much fluoride in the drinking water because it adversely affects our skeletons and particularly our teeth. A small amount of fluoride prevents cavities. When we get over 4 milligrams per liter, it will attack teeth and have negative skeletal effects. So we have an MCL for fluoride. Selenium, another inorganic chemical that we have an MCL of. Selenium can get into water based on the geology of the parent material in the local area, mining, smelting, things like that. We know that high concentrations of selenium adversely affect a person's liver, and thus we have an MCL of 0.05 milligrams per liter. Let's go down and do asbestos. Asbestos is used in insulation, or was used in insulation. If the asbestos fibers get into the water supply, it has been shown to cause cancer. Most people get cancer from asbestos by inhaling it from the air, but we can get asbestos in water supplies. And we actually have an MCL, which is simply a certain number of fibers per liter in the water. So there's other inorganic chemicals that I'm not going to show you detail on, but we do have primary standards for things like chromium, copper. Copper's a little controversial because it's actually a secondary standard. For barium, chromium, copper, cyanide, and nickel. So that's the category of inorganic chemicals. Let's look at a category that everybody's interested, microorganisms. A lot of microorganisms have no impact on us, but there's a few microorganisms that are basically pathogens. And many waterborne diseases are caused by microbes, and they're transmitted to humans by humans drinking water that is contaminated with these microbes. There's a lot of diseases out there that are attributed to poor drinking water quality. Typhoid fever, cholera, hepatitis are just 3 of dozens and dozens of diseases. And historically, we had lots of epidemics in cities in the Middle Ages because we didn't understand that there were microbes in the drinking water, and that's what transmitted diseases to people. Today, when we have sewer systems that break down, or we have poor sanitation, we can still pick up some of these bacterial diseases. A picture that I took off the internet, they have a cholera epidemic going on in Yemen right now. Because of the war and the infrastructure being poor, there's a lot of leakage in sewage systems, and cholera bacteria, or the bacteria that causes cholera, gets in the drinking water, and people come down with cholera, even today. And this is a very sick kid, just an example of probably 20,000 people that have been victimized by cholera in Yemen today. So when we talk about bacteria, microbial contaminants, we're talking about bacteria specifically. Bacteria are the most common water contaminants. Individual bacteria are not assayed for in drinking water. If you go to your public water system and you ask them, do they test for typhoid fever? Do they test for cholera? No, they don't. They run a test for fecal contamination. They test for what are called coliform bacteria. Coliform bacteria are basically an indicator bacteria, which tells us if our water has been contaminated with human or animal waste. If our water has been contaminated with human or animal waste, we probably have some pathogens that can cause human diseases. So all public water systems do a coliform test looking for pathogenic bacteria. Coliforms are a simple test. All public water supply systems are required to run it. Depending on the size of the public water system, water samples for coliforms are taken anywhere from 1 to 15 times a month. And basically they have a test where they look for they look for coliform bacteria, and they want no more than 1 coliform bacteria per 100 milliliters of water sample. Now, in the bigger cities, what they do is they will take, maybe 20, 25 samples over the month, and they can't find coliforms in more than 5% of the samples. If they do, they have to modify the water system so the public is not adversely impacted health-wise. This is called a presence-absent method. For instance, if you live in a community with a public water system and you have received from your public water supply system what's called a boil water order. A boil water order means that they found too many coliform bacteria in your water supply, and they're recommended that you boil your water before you drink it. Now, the public water system can rectify this problem by putting more chlorine in your drinking water. And that's what they do. If they see a presence of coliform bacteria, they add more chlorine to the water, and that usually solves the problem. Another type of microbe that's a really difficult microbe to deal with are a class of microbes that we call protozoa. They're a major problem. They're hard to kill. And in the United States, protozoa tend to be a bigger problem for public water supply systems than bacteria. There's 2 really famous protozoa. One is called Giardia. A lot of people call that backpacker's disease. And the other one is called Cryptosporidium. Giardia and Cryptosporidium are major problems in drinking water supplies that come from surface waters. Protozoa are bigger, quite a bit bigger than bacteria. They have weird shapes. Here's some example of some protozoa. They're larger than bacteria, and the thing that makes them really difficult is Giardia. Giardia of the genus species Lambilla is simply known as Giardia. We also call it backpacker's disease, and backpackers and hikers often get Giardia from drinking untreated water when they go hiking in the backcountry. A lot of animals have Giardia in their intestinal systems, and if they contaminate what we think are pristine lakes and rivers, and we drink the water without treating it, we can get intestinal inflammation. We can get bloating, gas, diarrhea, and an attack of Giardia can last a person anywhere from 1 to 10 days. It's pretty uncomfortable. It's a worldwide problem. So never drink pristine, what you think is pristine water out in the backcountry, because it might have Giardia in it. This is a worldwide problem. It's not a U.S. problem. It's worldwide. Here's a picture of Giardia. It almost looks like a science fiction thing. It looks like it almost looks like a face. It looks like something you might see in one of the Halloween type movies. The other protozoa that's really important is called Cryptosporidium. We have a specific genus and species of Cryptosporidium that's harmful to humans. Cryptosporidium lives in the intestines of animals. Humans get the disease by ingesting water that is contaminated with Cryptosporidium. Cryptosporidium is not very cute either. Here's a Cryptosporidium in a shell. That shell is very hard. It's very difficult for chlorine to penetrate it and kill it. If a human ingests Cryptosporidium in their drinking water and they get sick, we call the disease cryptosporidiosis. It causes severe diarrhea in humans, and it's often accompanied by vomiting, and it can last anywhere from 6 to 30 days. The symptoms can last several weeks. You can vomit and have diarrhea. Just, you might as well just stay in the bathroom for 10 days. What's really tough about cryptosporidium is if it gets in the water supply, normal water treatment doesn't kill it. There was an example in 1991 or 1992 when 400,000 people developed cryptosporidiosis overnight, basically in Milwaukee, Wisconsin. The drinking water supply got contaminated with cryptosporidium. 400,000 people got sick overnight. 100,000 of them had to go to hospitals. A few people died. Cryptosporidium is a surface water problem because, remember, it's found in the intestines of animals. So if you've got animals grazing in the watershed, they defecate, some of that can wander off into the water supply. Cryptosporidium is probably the main reason that when a community has a choice between surface water or groundwater to service the public, communities prefer to provide consumers with groundwater because groundwater doesn't have cryptosporidium in it. For instance, if we look in Idaho, we look in Coeur d'Alene, the water source for drinking water source in the Coeur d'Alene area is the Rathlin Prairie Aquifer. It's groundwater. They've got all that water in Lake Coeur d'Alene, but they don't want to use the Lake Coeur d'Alene water because it might have cryptosporidium, and it's really difficult to remove from the water. Boise, Idaho, biggest city in the state, on the Boise River. The city doesn't use Boise River water to provide water for its citizens. It uses groundwater. One of the reasons is they want to make sure they don't have cryptosporidium. Communities have found probably the best way to treat cryptosporidium is simply by filtering. You can use a small millipore filter to filter out the cryptosporidium, but it's really expensive to move the water through these filters. It raises the price of water considerably. Another drinking water contaminant I'm going to mention is viruses. Viruses are very common in water. When the Safe Drinking Water Act was passed in 1974, we didn't know very much about viruses in water. We still don't know very much about viruses in water today. We worry about them, but there isn't a lot of solid evidence. Here's a cute little virus under a microscope. It looks cute, but the impact on humans we don't know in our drinking water supplies. There are other things, other microbes that might be present in our drinking water supplies that we need to be leery of. One category would be algae. Still, we don't have a lot of information there. So I'm going to close this lecture by just briefly recapping that we talked about 3 of the primary contaminants that are regulated. We talked about the organic chemicals, the inorganic chemicals, and the microbes. Thank you for your attention. Control is they go into a resting stage, and in this resting stage, they have a hard shell. And when they're in their hard shell resting, it's very hard to kill them because chlorine can't penetrate that hard shell and kill them. And because of that, protozoa have made more urban residents sick in the United States than bacteria in the last 30 years. They've caused some major problems in the United States. Let's look at 2 of the protozoa. We'll start with water system. There are national drinking water standards, and I'd like to talk about those today. We have 2 types of standards. We have primary standards and we have secondary standards. Now, based on the National Drinking Water Standard,